So in the last group of lectures, we talked a lot about graphing lines. A line like this, for instance, could have the form y equals mx plus b. Or we had some other forms, y minus y1 equals m times x minus x1, ax plus by equals c. But all of these had one thing in common, and that is that the x was to the first power. And things where the x is just to the first power, we call linear, and linear functions graph as lines. I use the word function because a line in y equals mx plus b form or any other form is going to be a function. A function has no repeating x values. In other words, if this were on a larger graph, for whatever this x value is here, there will be no more than one point on the line that satisfies that. A line doesn't do this. It's a curve. It could be a graph of something, that's fine. But this wouldn't be a function. Because for, say, this x value here, there's that y value, and there's that y value, and there's that y value. That's where that vertical line test comes from. If you can draw a line and it hits in more than one spot, vertical line, that means there's an x value that has multiple different outputs. It wouldn't be a function. But as long as our line is y equals something and the something only has an x to the first power in it, then we can have positive slope things. I'm not going to draw slope guy again, don't worry. Negative slope things. Or even horizontal lines, because that would be y equals some number. These will always be functions. And that means instead of y equals, we can write f of x equals. It's like a special club, the function club. A vertical line would itself fail the vertical line test. But what's the equation for a vertical line? That's x equals something that doesn't involve y. So we can't solve it for y. So me saying it has to have y equals means that I'm right. Okay. Why am I reviewing all this stuff from the last chapter? Well, these types of lines are the first in the group of functions that we're going to examine today. We are going to learn about some basic functions, what their shape is, and we're going to memorize them. When I was in high school, my algebra teacher, Algebra 2, Mr. Martinko, Tink, he used to have these basic functions on the wall, on these posters that he drew up, and he would call them the poster kids. So today, we're going to learn the poster kids. Linear functions. And the special case of the linear function, the constant function. Linear functions will have a standardized form, f of x equals mx plus b. Constant function, well, that's a slope of 0. That means the m is 0, which means that term goes away. So f of x equals b. So the constant function, that's a special case of the linear function. What's so special about it? If the slope is 0. Linear functions, graph as lines. We did all that stuff in the previous lecture group. One very specific linear function we're going to look at is going to be this. The identity function. The identity function when we see the word identity in math, it should make us think of another word, itself. The identity function is f of x equals x, or y equals x. It's the function where our input is x, and the output is itself, x, itself, the identity function. If we made an XY table, and I'm making a point of showing it's an XY table, but since we're talking about it as a function, x f of x means the exact same thing as xy. So don't think it's like more complicated. If we had some x values, -2, -1, 0, 1, 2, the y values, the output of the function, would be itself. In other words, if we had f of -1, then we're plugging -1 in for x. When we plug -1 in for x, we get f of -1 is -1. The input of the function f, when x is -1, gives us an output of -1. F of x is -1 when x is -1. Okay. We know how to plug things in at this point. That's the last group of lectures. The important thing for today about the identity function is going to be the graph of it. This is like y equals mx plus b if b was 0 and m was 1. Y equals 1x plus 0, y-intercept of 0, and a slope of 1. This is the same thing we would get if we were just plotting the points. 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. So linear equations graph as lines. Let's talk about quadratic functions. These graph as parabolas. So these things. The parent function here is going to be f of x equals x squared. So y equals x squared. Our inputs get squared, and we'll get our outputs. Quadratic functions are squaring functions. The x is squared. So if I made a table for some points, xf of x, and I want some negatives, 0, some positives, and I start plugging these in, finding f of negative 2 would be negative 2 squared, and negative 2 squared is positive 4. F of negative 1 would be negative 1 squared. Negative 1 times negative 1, positive 1. F of 0 would be 0 squared. F of 1 would be 1 squared. F of 2 would be 2 squared. Negative 2, positive 4. Negative 1, positive 1. 0, 0. 1, 1. 2, 4. Parabola. Next, the cubic function. Don't worry, this is going to pick up. It's not all going to be fun drawing pictures today. The cubic function. I mean, it's going to be kind of fun drawing pictures. This is f of x equals x cubed. Let's see what this shape is by doing a table. X, f of x. I'll do some negatives, 0, and some positives. if I find f of negative 2 here, well, when we cube a negative, it stays negative. This is going to be negative 8. Negative 1 cubed would be negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1. Positive 2, positive 8. So this shape is like a stretched parabola that's been taken in 2 different directions. It's this shape. We're just going to call it the cubic. It's cubic. Next up, it's going to be the square root function. F of x equals the square root of x. When I make my table this time, normally I put negatives, 0, positives. Here, negatives aren't going to do anything. They're literally not going to do anything because I can't take the square root of a negative number. Not in the real number system. And when we're graphing, that is the real number system. It's not complex. There's no such thing as I on the XY plane. So I'm going to skip the negatives and I'm just going to start with 0. I'm going to be creative about the things that I pick. I'm going to be smart. If I put 1, yeah, I can take the square root of 1. That's a good pick. But if I put 2 like I usually do, that's the square root of 2. That's not going to be nice to graph. What's the next thing I can take the square root of? 4. And then 9. If I wanted another point, I'd pick 16, and then 25, and then 36, and then 49. Because square roots of perfect squares, those are nice numbers. The square root of 0, f of 0 would be the square root of 0. That's 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Now, you might be asking, what about the negatives? Well, normally, when we're solving an equation, if we had, say, x squared equals 9, and we took the square root of both sides, we would have plus or minus 3 as the answer. But Here, we're not solving, we're evaluating. We're taking a pre-existing radical x, and we're saying, hey, instead of x, all of a sudden, this is 9. What is this? And since we're explicitly being asked, what is radical 9, and there's not a minus before it, that means we only use the positive answer. Now I'm going to show something related to that in a second, but I want to get these points up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And 1, 2, 3. That's enough there. So 0, 0, 1, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3. There we go. So that looks kind of something like this. And it's because of my drawing that it kind of looks like a line, but it's not a line. It's making this shape. And it's starting at 0, 0. Let me make this a little clearer because I want that shape to be more visible. After all, we're playing with shapes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 0, 0, 1, 1, 2, 3, 4, 2. 9, 3. And it's going to keep getting shallower and shallower, not steeper. It's getting shallower. Does that look like anything? If I turned it on its side, you'd have half of a parabola. If I turn this on its side, you'd have the square root. There's the squaring function graphed on the same one. And it makes sense that these shapes are similar because one's squaring and one's square rooting. So as the squaring one gets steeper and steeper and steeper as you go, the square root one gets more and more shallow. So remember I said I'd come back and show you another one. This one is not a function. This one is going to be a full parabola on its side. And you can see why that would not be a function. Fails the vertical line test. This would be the relation x equals y squared. And there, our y squared. Y squared means not a function. This is different than this. And in order to make my point, I'm going to change the f of x back to y, because you might be going, yeah, one has y, one has f of x. Of course they're different. No, these are different too. Because here, it's explicitly the positive radical. The square root sign is already there. Here, the square root sign is not there already. So when we solve it for y and take the square root of both sides, we have to remember to take the plus or minus. And it's that negative square root that fills in the bottom. So far, our functions, we've got our lines, we've got our parabolas, we've got our cubics, we've got our square roots. Next up is going to be the cube root. The cube root function is going to be f of x equals the cube root of x. So I'm going to use smart x picking again. I can take cube roots of negatives. We used perfect squares for x's for the square root function. Let's use perfect cubes. -8, -1, 0, 1, and 8. The cube root of -8 is -2. The cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. So let's see how we get this shape I promised you. I need 1, 2, 3, 4, 5, 6, 7, 8 that way. 8 that way. I need 2 up and I need 2 down. -8, -2. -1, -1. 0, 0. 1, 1. 8, 2. And that's the graph. The absolute value function. It's going to be f of x equals, you guessed it, the absolute value of x. Table. I'll pick some negatives. 0. Some positives. It's a function, so instead of y, we'll call it f of x. The absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. If I plot these three, 0, 0, 1, 1, 2, 2, that part of it looks very much like the identity function. Is this the reference? No, it's not. But these, the negative x's, are also giving positive y values. So instead of it being continuing on like the identity function, it goes that way instead. So the absolute value function has this equation and this shape. Okay, ready for this all to come together. If we want to take a graph and move it up or down k units, the function changes by either adding or subtracting k to it. What does this mean? Well, let's say, so up k, down k. Let's say we had the function g of x equals the absolute value of x minus 3. And we wanted to graph this. Well, we would ask, what is the parent function? And the parent function, since we have an absolute value in here, would be the absolute value of x. Okay. Parent function's the absolute value of x. We know what that looks like. That looks like that. So when I'm saying you need to know those shapes, you need to know that something that has a function that looks like that has a graph that looks like that. When we see a function that has an absolute value in it, we know the absolute value parent function is the absolute value and that it looks like this. See this down 3, this minus 3. Taking that and subtracting 3 is going to move it 1, 2, 3 down. And that's how you move graphs up and down. Let's look at another. Let's say we had h of x equals x squared plus 2. Ask yourself, what's the parent graph? Well, this is a squared. So the parent graph is f of x equals x squared. What's happening to the x squared? We're adding 2. Well, what does that mean? It means the original x squared graph looks like that, If we move it up 2, it'll look like that. How do we know where to draw? Well, the original had 0, 0. That'll be our new starting point, and everything gets moved up 2. So if we went right 1, up 1 to get to 1, 1, here we would go right 1, up 1 to get to that next point, and we draw our parabola through it. I wanted to make sure I'm using the same letters as the book. We talked about up and down. Let's talk about left and right. It's going to be adding and subtracting again. But this time, instead of adding or subtracting to the whole function, you're just going to add or subtract to the x itself. So, what does this mean? And I want you to notice the left is plus, right is minus. You might instinctively switch it because of the fact that a number line has pluses on the right and negatives to the left. But it's the opposite of what you'd think it is. So if you want to remember that left and right is the opposite of what you want to think it is, and you want to think it's this way, then switch it, and right is minus and left is plus. Just like the other things we've dealt with H and K for circles, for instance. X minus a negative becoming plus, that's why the plus is actually left. It's one of those minus and negative things. But anyway, we want to move it left, that's plus. If we want to move it right, that's minus. Let's take a look at a g of x equals x plus 1 squared. Well, this is a squaring function. It's quadratic. We've got a square on it. So that means the parent function is f of x equals x squared. And we know what that looks like. That looks like this. Plus 1, when it's added to the x and not to the square, not to the whole function. plus 1, that's going to move to the left 1. So it's our normal quadratic moved left 1. What if we want to do both at the same time? We can do that. Let's say we have p of x equals the square root of x minus 3, where the x minus 3 is under the radical, and then minus 2, where the minus 2 is outside of the radical. Well, the parent function, f of x, that's going to be the square root of x. And we know what that looks like. The square root of x looks like this. This minus 2 on the outside, that's telling us to go down 2. This minus 3 on the inside that's just subtracted from the x, that's telling us to go right 3. So from the starting point, we go down 2, we go right 1, 2, 3, and there's our new starting point. Then up 1 over 1, and then all the same count overs as the parent graph. It's like we take the parent graph and we subtract 3 minus 3. We move it to the right 3 and we move it down 2. So this point, whatever it is, we would move it right 3, down 2. So maybe I should have been up here somewhere. But anyway, I'm just drawing shapes. Could we do one more of these? Yes, absolutely. Q of x equals the square root of x plus 2 with the plus 2 with the x, and then on the outside, minus 5. Watch this. We know the shape of the square root. It's the that thing. So instead of it 0, 0, that minus 5 on the outside is down 5. That plus 2 with the x, it's the opposite of what I want. So that's going to be left. So if I go down 5 from the normal starting point and left 2, there's my new starting point. That's my new second point. So it's something like that. Assuming that this is just up, down, left, right movements, what would this be? Assuming it's just up, down, left, right. Well, it's an absolute value. 1, 2, 3. It's moved up 3. And it's been moved 1, 2, 3, 4 to the right. And I'll give it a name. Call it C. That's all you do. I'm going to come do that thing I wanted to show you now. I want to take a look at h of x equals x plus 3. If this was y equals mx plus b, then m, the slope would be 1, and the y-intercept would be 3. 1, 2, 3. And then we'd go up 1, over 1. Or down 1, left 1. So my question to you is this an upwards shift of the identity function? F of x equals x? Because we're adding 3 to the whole thing, so it should be up 3. But wait a minute. This can be considered just adding 3 to the x. So is it left 3? Is it up 3 or left 3? Well, you can see if I put the identity function in, it doesn't matter. It is both 1, 2, left 3 and a 1, 2, up 3. The identity function, since all it is an x, since there's no symbol around the x, up movement is the same as left movement. And that's what makes this special enough to give it its own category separate from just a regular linear equation. Okay? So with the identity function, a plus 3 here, that can be considered up 3 or left 3. Let's start with our line. Even without talking about a function, let's just talk about the graph of y equals 2x. We know we could imagine this in slope-intercept form, y equals mx plus a b. If we put a plus 0 there, that makes clear that our y-intercept is 0. M is 2. That's our slope. 2 is 2 over 1. So that's either positive 2 over positive 1. But what's another way to get 2? Negative 2 over negative 1. So we either go up 2 right 1, or we go down 2 left 1. Remember, that's how we did slope. So from this point, we can go up to right 1, or we can go down to left 1. Either way, our slope of 2 gives us a line that is steeper than if we had our identity graph, the normal y equals x. So y equals x, the identity would be more like this. If we have y equals 2x, that's getting steeper. Imagine driving a car, you already would not want to be going up the blue line. Now this black line, that's making it even worse. And in fact, the bigger the slope gets, 4x, 5x, 6x, the steeper and steeper and steeper the line gets. Another way, though, to think of the line getting steeper from blue to black could be imagining stretching it vertically. This will be more clear, I think, if we take a look at an absolute value function. So from our parent graphs, we know y equals the square root of x, or talking about them like functions, f of x equals the absolute value of x. We know that that graph, from what we did last time, is an absolute value v like in value, where it goes up 1 over 1 in both upward directions. It's basically the identity graph here and then the identity graph flipped upward there. And we got this shape by plugging in values into a table, where if we put -1 in for x, we get 1 out for y, because the absolute value of -1 is 1. And if we put 1 in, the absolute value of 1 is 1. And if we put 0 in, the absolute value of 0 is 0. And we can get that graph. Now, over top of that, I'm going to put a graph G. And I'm going to say G of x is 2 times the absolute value of x. And this table, x, G of x, I'll put those same x values in, -1, 0, and 1. So I have to remember I adjusted the camera since last time. I put it in every time and then just kind of hope it still works. One day I'm going to go to do one of these and all my magical rigory is going to not work and we're going to be in a bind. But for now, everything's still working. So our inputs, and then for G of x, we're going to take the absolute value and multiply what we get by 2. So the absolute value of -1 is 1 times 2 is +2. The absolute value of 0 is 0 times 2 is 0. The absolute value of 1 is 1 times 2, +2. So here we still have the point at 0, 0, but -1, 2 is the point, and 1, 2 is the point. This graph has been vertically stretched. So when we're multiplying by a whole number, that stretches the graph vertically. What if instead of a 2 on the outside, we had a 1/2 on the outside? So instead of a number greater than 1, but still positive, let's have a number less than 1, but still positive. So in other words, a number between 0 and 1, less than 1, but greater than 0. In other words, our fractions, our proper fractions. Well, if on the base graph, let me draw that again. If on the base graph we have our 0, 1, -1, blah, blah. And we want to find those same points. So an x, y, or an x, g of x table, -1, 0, and 1. We'll take the absolute value and then take a half. The absolute value of -1 is 1. 1 times 1/2 is 1/2. The absolute value of 0 is 0. 0 times 1/2 is 0. The absolute value of +1 is 1 times 1/2 is 1/2. So here, instead of going up to 1 on the y, the values are actually at 1/2. Instead of a vertical stretch from blue to black, we now have a vertical shrink. It's like, imagine the blue graph is in a meat presser and it's squishing it down. It's getting shallower instead of steeper. So in general, if we take a parent function and that's a cursive F. I'm going to keep wanting to draw that. If we take a function and we make sure I use a consistent letter, it'll be A, multiply by a constant, multiply the whole function by the constant. If A is greater than 1, if it's like 2, 3, 4, whatever, then it's a vertical stretch. However, if A is one of our proper fractions, if A is between 0 and 1, then it's a vertical shrink. Now, there's a funny thing about looking at things vertically and then looking at them horizontally. Times like this, I wish I had some gack or some slime or something that I could squeeze and get, you know, like a stress ball or something. But I'm looking around. Do I have anything fun for right now? Nope. If I am vertically pushing something down, again, imagine a burger on a grill. If you push it down, what happens to the outside? Well, it's like it's stretching. A vertical shrink is the same as a horizontal stretch. A horizontal, let's see, vertical shrink is a horizontal stretch. A vertical stretch would be a horizontal shrink. And this is going to be, so a vertical stretch is the same as a horizontal shrink. And a vertical shrink, that's the same as a horizontal stretch. Vertical, up and down. Moving up and down was adding to the whole fraction. Horizontal, left and right. Left and right is adding or subtracting to the x and only the x. So let's take a look at this graph. G of x equals the absolute value of 2x. My hand froze. There we go. So now instead of the 2 being outside, the 2 is inside. When the 2 was on the outside, it was a vertical stretch. Let's see what happens when the 2 is on the inside with the x instead of outside of the whole function. That should be moving things from a vertical talk to a horizontal talk. So the 2 with the x, let's make an x y and x g of x table again. Let's look at -1, 0, and 1. -1 times 2 is -2. The absolute value of -2 is +2. 2 times 0 is 0. Absolute value of 0 is 0. 2 times 1 is 2. Absolute value of 2 is 2. This is the same stuff for the vertical stretch. It's the same graph. But a vertical stretch, that's what we would call it if the 2 was on the outside. The 2 is on the inside with the x. A vertical stretch would be described as a horizontal shrink in this case. Because when it's with the x, that's left and right, that's talking about horizontal stuff. When it's on the outside, that's up and down. That's talking about vertical stuff. But they are the same thing, a vertical stretch and a horizontal shrink. How do we graph it? We make a table. So we'll always do our stretches and shrinks by using the parent graph, but then finding new points to the left and the right of the starting point.